All right, let's look at this example problem and actually start to work through it. All right, so I mentioned thinking of it as a unit conversion problem. So really, we have a certain number of nanocoulombs, which we ultimately want to get to how many electrons, right? And so we want to think, we know how many electrons are in a coulomb, so let's get nanocoulombs to coulombs, and then we can go coulombs to electrons. Remember, electrons is really just a label on a number, right? So it's no different than a unit. And so here's my setup. Well, let's write what we have. We start with negative 40 nanocoulombs, and we can set up a fence post. I want to get rid of nano. Well, there's nanocoulombs, and there's coulombs. Now, the way these metric tables work, nano, that little n literally means 10 to the negative 19. So I can put 10 to the negative 9, sorry, 10 to the negative 9, not 19, over 1. And that's going to get me out of nanocoulombs and into coulombs. Nano is the same as 10 to the negative 9. Now from here, it's just about getting from coulombs to electrons. And here I can use either one of my conversion factors. We know 1 electron is negative 1.6 times 10 to the negative 19 coulombs. And we also know that 1 coulomb is 6.25 times 10 to the 18 electrons. So depending on how we want to work it, I can do it this way. 1 coulomb is negative 1.6 times 10 to the negative 19. Or I can do this step. You still have to have E on the top and C on the bottom, but I can say that 1 coulomb is 6.25 times 10 to the 18 electrons. And no matter how I slice it, when I put it in my calculator, now I can just multiply straight across. 40 times 10 raised to the negative 9. Now, think about what we did there. We multiplied times 10 to the negative 9. Isn't that what the double E feature does? So I can do the same thing right there to get that answer. And from here, I either got to divide by 1.6 second e to the negative 19 to get my answer. Or if I were to multiply 4e to the negative 8 times that 6.25, I should get the same value. So 2.5 times 10 to the 11 electrons. That's a lot. 10 to the 9 is a billion, right? So this is 250 billion electrons. That's not total electrons in the balloon. That's just the amount of extra ones that were wiped off, right? So this little bit of charge in the scale of nanocoulombs has 250 billion electrons associated with it. All right, so it just gives you the scale of how easy and how many electrons there are in these materials and how easy they are to wipe off. I also want to go back and point out something about how we can convert from nanocoulombs to coulombs. And show you just a really simple trick, and it really, if you look at your fence post, it should be obvious how it plays out. But if I have, let's say I have 60 millicoulombs. If I want to convert, really what I'm saying is 60 times m times c, if you look at like an algebra problem. And since m is the same as 10 to the negative 3, I really have 60 times 10 to the negative 3 times c, right? And so that's how I would convert to coulombs. M literally is the same as that, right? So if you had another example, if I had, let's say I had 251 kilometers of distance. Well, then that's 251 times whatever k is. Well, k is a prefix for 1,000, or 10 to the positive 3. And I still have meters. And so all I have to do is take 251 second e to the 3, or multiply it by 1,000, and that's how many meters I have, right? Which makes sense, should be a lot of meters. All right, so we're going to see this type of conversion a lot in a problem, and we can avoid even having to deal with a fence post if I just understand how that plays out. Now, one more little calculation we can do. If that's how many electrons have been added to the balloon, well, then technically we've changed the mass of the balloon itself. We gave it more mass because each electron has a little bit of mass associated with it. All right, so I can take this a step further and ask a follow-up question. How much mass did the balloon gain? Well, if you do a little Google search, you'll find that one electron has 9.11 times 10 to the negative 31 kilograms of mass. That's how much mass one electron is. A really small amount. That's a lot of zeros in front of that 9. And so, once again, we just have a simple conversion. I know we have 2.5 times 10 to the 11 electrons that are extra on that balloon. And all I want to do is go from electrons to kilograms. And 1 kilogram is 9.11 times 10 to the negative 31. And in my calculator, 2.5 second e to the 11 times 9.11 second e to the negative 31. And we get a really small amount of mass, 2.28 times 10 to the negative 19. So we've added 250 billion electrons, but haven't changed that mass by very much, as we would expect. The balloon doesn't look much heavier. So just a nice quick example of taking charge, determining how many extra or missing electrons are associated with that charge. Obviously, if it's a positive charge, you can quantify exactly how many missing electrons you have and how much mass it lost. So just, again, examples of some things we'll be doing, some skills we'll need to have. And of course, you'll be given any of these problems on a test. And you might even be given some of these metric prefixes. But I would get in the habit of memorizing centi, milli, micro, nano, and maybe even pico if you can remember that. And they're all multiples of 3 except for centi. All right, so let's get back to understanding what was happening in our mini lab. And I think it's always fascinating. You see all these different materials get rubbed together and then all these different interactions. And what you really need to understand, as we talked about a little bit earlier, is this sense of balance, right? In our universe, all materials seek balance. And this goes for all kinds of realms. I mean, you can even, look at ecosystems, the animal food chain. It's all based on balance. You mess with one thing and it screws up the whole balance of everything else. Well, the same thing goes here with electricity and charge, right? So balance is an important idea that we have to understand. And when it comes to charge, balance, there's a term for having balance. We call that charge equilibrium. Just another term, right? And all that means is that the number of protons are equal to the number of electrons. When that's the case, I have no charge, and we are in charge equilibrium, or we would say that material is neutrally charged, right? Not charged at all. It's neutral. All right, so just some different terminology. And with that in mind, if these materials want to find balance, then there must be some driving forces that are pushing or pulling them in the direction of that balance, right? And that's where we get these attraction and repulsion forces, right? So in order to seek balance, there's forces that exist. And there are forces of attraction and repulsion. That exist to achieve that balance. And if you think about it, it makes sense why opposites should attract. This is something I think most people understand. It's kind of a cliche, right? However, if you think about two materials, if one's positive and one's negative, well, that negative material has all these extra electrons on it. They do not want to be in a place where they're not balanced. So they want to go somewhere. Well, they have to go somewhere that can accept those extra electrons. Well, if you bring a positive material near it, that positive material really wants electrons, right? So you get this natural attraction of opposite charges. And you'll see that materials with opposite charges will actually physically be pulled together. And you see this force of attraction. And on the flip side, if you have materials that have this excess of electrons, meaning they're negatively charged, or they're both missing electrons, well, they definitely don't want to be near each other because that's just making the situation worse, right? Too many electrons in one place, they want to get away from each other, right? So anything with what we would determine as like charges or the same charges, whether it's positive or negative, if they are the same charge, you would get those materials repelling. And what determines how these electrons move is really the material properties of and the atoms that make up the materials. Right? So we understand opposites attract, like charges repel, but how do the electrons actually get onto these objects to begin with or move? Right? And so let's look at the material properties, because it's the material properties that determine how electrons will move. For you guys that are familiar with the periodic table, you learn that certain materials on that table are in certain locations based on some of these properties we're going to look at. Some of them, if you think of electrons in these valence shells, have more freely available electrons that could be transferred back and forth, whereas some others are really tightly holding on to their electrons. They've got a full shell and they don't want to give anything up. Right? And so certain materials lie in different spots on those tables, and as a result, you see different properties with these materials that are associated with that. So the first is these materials that really easily allow electrons to flow between them. And we call these materials conductors. In conductors, electrons can flow freely through the material. They are a material in which electrons can flow freely. Now, if you want to think of some examples, the most common one that we think of as conducting materials of electricity, sorry, I jumped here between pages. Those would be metals. And not all metals are created equal. Some conduct better than others. In rank order, some of the best conductors, gold is a really good conductor of electricity, followed by silver, copper, and aluminum. And if you look at it, some are more rare than others, some cost more than others. Gold is obviously probably the most expensive on that list. And so depending on what you need to do as far as how you want to transfer those electrons, you can pick a material that will be a better conductor. So any of you guys that are into audio video equipment, if you're buying an HDMI cable and you want a really good signal quality, especially if it's a long cable, you're going to spend a lot of money for a good cable. And if you look at that cable, the reason it costs so much is because it likely will have some kind of gold-plated connector or even gold woven within the conducting material in the wire itself. If you look at long power lines, a lot of those are made of aluminum, right? A cheaper material. that's lightweight that can be strung over long distances. And your typical wires in your home are going to be copper. So you have all these different types of materials, all of which conduct electrons and allow them to flow easily. On the flip side, you have other materials on the spectrum that do the opposite. They hold on to their electrons and do not allow them to move very freely, right? And these materials are ones that we put on objects to control the flow of these electrons to protect us from getting electrocuted. And so we would call these insulators. These again are materials in which the electrons are tightly bound to the atoms and do not move freely. So a lot of the materials in that video that were holding the charge would be considered insulators. So if you look at that video, you saw rubber, you saw plastic. Those are really good insulators. Rubber being the insulation on electrical wires. You saw glass. You even at times will see wood as a insulator. Right? And so these materials, if you were to rub them with a cloth or a material that would give up electrons, that material will hold on to those electrons, and those electrons will sit in that one spot. That balloon, those electrons will sit in that rubber and stay there. They won't transfer around the balloon. Whereas if that was a metal balloon, the electrons would spread out over the whole surface. Now, one thing I found interesting, I'm going to show you this guy's video. I learned a little bit something myself having watched it, because depending on what materials you have, some materials actually, and we'll speak more about insulators now because that's really what he was dealing with most of those activities, but these materials actually, some are more willing to give up electrons and some are more willing to take them. And there's a term that we can use and we use basically a ranking of these materials, and it's called a Triboelectric series. And as you'll see in the video, it has something to do with rubbing materials together. And all this is a list or a ranking of materials by their willingness to give up electrons. And this can be helpful to determine whether when you rub two materials together, you'll be creating a positive charge or a negative charge. So a good example, here's a list of materials that would be on a triboelectric series. And these aren't, this isn't every material, but some basic ones that you guys will interact with. Skin, glass, hair, I'm going to put like 7 or 8 of these on here. Nylon, wood, cotton, rubber, polyester, and PVC plastic. So this is a triboelectric series of materials. And what you need to understand is that a material, if you were to rub any of these two materials, the material that is higher on the list will be the one that gives up its electrons. When there's friction, when rubbed, the material higher on the list will give up electrons. And as a result, if it's the one giving up, what kind of charge would it have? Well, it would then be positively charged. Because it will be missing electrons now and therefore have a greater number of protons than electrons. All right, so for example, if I were to take, like he did in the video, we saw he took that glass tube and he rubbed it with a cloth. Like he had like a polyester cloth that he rubbed on the glass tube. All right, so if we took glass rubbed with polyester, well, based on where they're located on the list, we know that the glass will lose electrons. The glass will give electrons to the polyester. And as a result, when you take that glass tube and you bring it near an object, that glass tube is now positively charged and will react accordingly with the materials it interacts with. Right? So the glass is now positively charged, and therefore, if it gave up its electrons, well then the polyester cloth must then have gained electrons and now be negatively charged. So these are important concepts to understand when you start to watch these demonstrations that we did on Thursday. And I'm going to turn it over and let our physics teacher on YouTube take us through some of this, and you'll see some overlap. He'll be explaining some of these concepts, but hopefully now that we've touched it here in our notes, you have stuff you can work from here. And really, it's if you can understand all these demos and kind of visualize what's really happening with these electrons. Are they gaining? Are they losing? And you can start to make predictions. Well, then now you start to have an understanding of these electrostatic concepts.